so I hope he's trained well. And he's done a lot of interesting things, both in academia at CMU and Duke, and in industry at NEC, Akamai, and Emerald Innovations. And he's going to talk to us today about some of the work he's done recently at Emerald Innovations.
Thank you. Yeah, thanks, Cliff. So actually, it's super fun for me to be here because I've got a lot of old friends. Like, as Cliff mentioned, we were office mates for maybe three years in grad school. And Satish and I did our PhD defenses in the same room with the same committee back to back. And it was super hot in that room, and he went first. So my defense only took about 45 minutes. And yeah, so and Raj and I we lived together for a year when I was on sabbatical, and then at Akamai, and my former student Andrea is here, and my siblings. And so I know what you're thinking. Oh, that must be why they invited him. And mostly because of my connections. But as Cliff said, I spent the first 15 years of my career in the theoretical computer science community. I was working on algorithms. And then I got sucked into Akamai and became an engineering manager. I was head of engineering at Akamai. And I really enjoyed building big systems. And so when I went back to academia, I kind of switched my research area to systems. And 6 years ago, around this time, I had taken another sabbatical at MIT, and I got sucked into a different startup company called Emerald Innovations, which I'll tell you about. And so this talk is going to be a complete change of gears from everything you've seen so far in this boot camp, because we're not going to talk about memory architectures or anything related to computer architecture. We're going to kind of now look at things from an application level. The specific application is trying to gather information about the health of people in a room using wireless sensors. So what do I mean by this? So this is a picture of my apartment in Cambridge. And by the way, I'm no longer full-time at Emerald. I did that for 5 years. I've gone back to Duke, and so now I have a very part-time kind of advisory role with Emerald. But my role at Emerald was head of engineering, so I spent a lot of time trying to get this stuff to work. And so you can see on the wall here an Emerald sensor, and that's kind of typical deployment. It's facing a bed, and most of the Emerald sensors that are in the field are deployed like this, and they collect information about volunteer participants in clinical drug trials. And mostly, not always, but mostly they collect information while they're sleeping. But we'll see that also sometimes information while they're walking around their homes. So you put one of these devices on the wall, and the selling point that Emerald makes is that once it's mounted on the wall and connected to Wi-Fi, there's no longer any compliance requirement on the part of the participant. They don't have to remember to wear anything. They don't have to do anything. It just sort of silently collects data. So here's a demonstration, an early demonstration of what the device can do. This is one of, oh, and I should say, so Emerald was, it's an MIT spinoff. It was founded by Dina Katabi, Rahul Hariharan, Rumen Christoph, and Zach Kabalek. The latter three are former students of Dina, and then I was the next person to join after that. So it's the technology originally came out of Dina's lab at MIT. And this is one of her former students, who's Fadil Adib, who's now on the faculty at MIT. And he's just going to walk around the room, and you can see in the lower left-hand corner a position estimate, like where is Fadil. And so this is very simple. It's just representing his position in the room two-dimensionally as a dot. But we're going to see that just having this capability can tell us some things about participants in clinical trials. So, by the way, in this picture, you don't see the Emerald device because part of this demonstration was also that the device can see through walls. It's a radar device, and I'll explain how that works. And it's using radio waves, microwaves that are just above Wi-Fi, and they have the ability to penetrate walls. So I don't know, there's a wall somewhere and devices on the other side of that wall. So let's look at some data collected in I guess this is a trial or a study of Parkinson's disease. And I call this graph a tree ring diagram. And in this diagram, there's a 24-hour clock. So at the top we have midnight, and the bottom we have noon. So we're on European time here, like 2300 and so on, or military time. And each ring, which is colored, represents one day. And the colors show where this person is located in the room. So this is an assisted living facility, a person who's suffering from Parkinson's. And a couple things you can see in this chart. First of all, this person doesn't spend that much time in bed. There's something abnormal probably about the sleep pattern. You can see that it's very, typically the person is getting into bed around 11 o'clock, right? Whoops, right here. And then they're up and out of bed, somewhere between 3 and 6. And then after they're out of bed, they sit in a chair. And they sit in the chair until 7, and they go to the bathroom at 7. So when we were discussing this with one of the doctors who was conducting this study, and we didn't know what to make of this, and the doctor immediately said, oh, well, this demonstrates that this participant is not able to go to the bathroom on their own. That is, they can't get themselves in there. And what's happening is that every morning a nurse comes to check on the participant at 7. That's why exactly 7 o'clock every day this person goes to the bathroom. And there's some other things you can see here that this participant really enjoyed the communal dinner, and so at 5 o'clock every day, the participant would go. And so there wouldn't be any data then, except for the participant wasn't feeling well for a few days, so stayed in his or her room on those days. So this is interesting because one of the advantages of this device is that it really gives you a lot of longitudinal data, right? You get every day, day after day. And in a typical study, a device will be placed in the home anywhere from a few weeks to even like maybe as long as a year. So the device is collecting a lot of data compared to some of the more traditional ways of collecting data about participants in clinical studies. Here's another graph showing some data from a Parkinson's study, and it's showing gait speed, like how fast is this person walking at different times of day, and this is averaged over some period of time. And you can see, so it might be that there isn't so much data for 4 a.m., but there's some. And you can see that at certain times of day, the person walks much faster than other times of day. Well, why is that? And the reason is that this person is taking the standard medication called levodopa, and these are the times when the person takes the medication. And what you can see is that the medication is working as expected, that after this participant takes the medication, their gait speed increases for a while and the medication starts to wear off, they take it again, and that's, it's doing what it's supposed to do. So these are two examples where simply tracking the position of the person in the room or how fast that position is changing can tell you some medically interesting things about the person. So that's cool. That's a simple capability, but it has interesting, potentially gives you interesting data. So how does this work? I think this is pretty cool. So I mentioned that this is a human radar device. And so inside the Emerald device, there's an array of antennas, and there's a radio transceiver, and it sends signals out, and they bounce off the things in the room, including the people in the room, and then the signals come back. And the first thing you'd like to know is, okay, well, how far away is the person from the device? Before we try to do anything more fancy than that, how far away is the person from the device? And so here we use the fact that the speed of light is constant and known, and so if we can measure how long it takes for the signal to leave the device, hit the person, and bounce back, we know how far away the person was. You might think that, okay, well, this shouldn't be too hard. We'll start a stopwatch and we'll send out a pulse, and we'll wait and see when it comes back, and we'll stop the stopwatch. The problem, yeah, you can't do that because the speed of light's really fast, okay? You just can't do that. We're gonna have to have some really analog circuitry to figure out how to do this. And we wanna get the reflection time, but we're not gonna measure it directly. Instead, we're gonna use a technique. This is one of a number of different types of radar. It's called frequency modulated continuous wave radar. And here's the idea. I mentioned that we're gonna send a radio signal. This radio signal is gonna be a pure sine wave, but it's not gonna be at a fixed frequency. It's gonna start at one frequency and like let's say 6 gigahertz, and very rapidly it's gonna ramp up to 7.8 gigahertz in a very clean linear fashion. Okay, so if we look at the frequency over time, we're gonna start with one of the transmit antennas in the array. We're gonna start a 6 gigahertz sine wave, and we're gonna start ramping up the frequency to 7.8, then we're gonna stop. So we send out this signal, and it's gonna go out, bounce off something, and come back. And by the time it comes back, the frequency that we're transmitting at will now be a little bit higher than the frequency we sent at. And if we can measure how much the frequency has changed, then we know how far that signal went before it came back, right? So we're trying to measure this, well, we will measure this change in frequency, and since we know the rate of change, that'll tell us how much time has elapsed. That's the whole idea behind frequency modulated continuous wave radar. Okay, so how do we measure change of frequency? Well, that turns out not to be too hard. So it turns out there's a standard analog component called a mixer, and you can pass it 2 signals, and it will spit out the difference in frequencies. And how does that work? Well, it turns out that if you just take, let's say, 2 pure cosine signals at different frequencies, and you just multiply them together, what comes out is the sum of the difference and the sum, okay? And the sum is some giant frequency we just filter out, and so we've got the difference, right? So we've got this mixer, and from the mixer, we filter out the high end here, and then we compute an FFT, and we look for where the large components are, and that tells us, like, what's the difference in frequency, which is the distance, tells us, directly the distance to the object. And by the way, here's the first plug for an algorithm. Okay, FFT, that's like the basic algorithm in signal processing, and yeah, it's really cool to actually see it in your code. So we're using an FFT there. Good. Now, one issue with what we've done so far is that if all I tell you is distance, that doesn't localize position very much, right? If I say, okay, well, right now I'm 24 feet away from Satish. Well, it's somewhere in some sphere, 24 feet in radius around me, but what about like really nailing down the position? So how do we do it as people? We've got 2 eyes, right? Well, that's why we have an array of antennas. We're gonna do multilateration, right? Sort of like stereo vision. So here's the idea. If one of my antennas says, yeah, my signal bounced off something at 2 meters, and then I have another antenna and it says, well, my signal bounced off at something at 2.1 meters. Another antenna says, well, mine bounced off something at 1.98 meters. Now you can kind of look at, and you know the relative positions of these antennas. They're fixed on the board. Now you can look at that and say, I think the object's there. That's the point that's kind of consistent with all of those readings. Okay, so once you can do distance using one, transmit receiver pair, you can start to do better localization. If you have the more pairs like this you have, the better. Okay, and so that's how that works. And there's the person. Now, actually, the signal is bouncing off everything in the room, not just people, right? But we don't care about the stuff that isn't moving. So you should think of this as it's like taking a video, snapshots, okay? Except that instead of being a video camera where like every pixel is giving you a color, Now every pixel is giving you a depth. Okay, we're going to know in sort of every direction how far did the signal go before it bounced back. And then we're going to only look for things that are moving. Okay, we're just going to ignore, we don't care about the table. We want to see people that are moving, or if you're not moving, you're still breathing. And we're going to see like a huge amount of effort has gone into being able to detect breathing signals. And one of the side effects is if you're standing there, as long as you're breathing, we can tell you're there. Okay, so we're going to filter away everything that isn't changing and just look for changes in the signal.
What if someone else comes into the room?
So that's a big thorny issue, okay? How do we make sure that we're collecting data only from the participant who we care about, right? So of course the best thing is if the person lives alone, or if they sleep alone in the bed, or at least they agree to always sleep on their side of the bed. Nevertheless, sometimes you have to distinguish between the person and other people, or the dog, or whatever. Okay, so what we do in that case is if we find out that this person lives with other people, which is common, for the first 2 weeks, the participant wears an ankle band, which has an accelerometer in it. And so we learn who the person is based on, for example, their gait, but also sort of their body size. And so we'll see a little bit of that. But that's super important because otherwise, the medical information wouldn't be useful if we don't know with high confidence that it's coming from the person we're trying to study. Yeah. So I kind of said there's no compliance issue, but that was sort of a white lie because if there is this training period if there's multiple people in the home. If the study requires us to differentiate like multiple people who might walk around in the same room. Okay. So let's look at something a little more sophisticated. So this is going to be reconstructing the pose in motion of multiple people in a room using a single Emerald device on the wall. Now there's a camera here taking a video, but that video is only used so you can see that what's being reconstructed actually matches what's going on. So these are some graduate students at MIT. And they're walking around, and then this is what's being reconstructed from the radio frequency data. So you can see we can actually do better than just position in the room. We can reconstruct pose, at least sort of stick figure pose. And we can now even see sort of some activities like sitting in a chair and getting up out of a chair. Okay, so how does this work? So here, we're going to use machine learning models, neural networks, to reconstruct the pose of everybody in the room. And that's the problem we're trying to solve. We've got this radio frequency signal we're collecting, and we're going to go from that to pose. And in particular, we're going to have a model of the body with 14 key points, something like this, and we want to take the RF signals and translate it into, pose like this at certain positions in the room over time. So one of the complications here is that at these frequencies, these microwave frequencies, the human body is specular. That's a word, I didn't know what that meant before. What specular means is that the radio signals bounce off the body the way a billiard ball bounces off the sides of a pool table. So whatever the angle of incidence is, when the radio wave hits your body, it bounces off the same way. Like basically your body is like a mirror at these radio frequencies. So that means that what bounces back to the device is going to depend on your orientation towards the device. And if you're walking, so here's a picture of a person, and which parts of, it's a little hard to tell what's going on here, but there's a person here, and at this instant, we're getting good reflections from some parts of the body, but not from other parts. And so the hope is that if somebody is walking through the room, while it's true that at any given instant, we'll only get reflections back to the device from some parts of the body, while the reflections from other parts, go somewhere else. or maybe annoyingly bounce off a few things and then go to the device. If the person's walking, then maybe over time, we see different parts of the body. And so what the machine learning model is going to do is it's going to look back across time, and it's going to try to fill in the missing parts in every frame. And so the hope is that we get something like this. And actually, the network architecture uses transformers, and in some ways it's a little bit, well, it's not very close to these large language models, but nevertheless, there's kind of this idea that you look back in the past and you try to get that to help you fill in things you can't currently see. These models are, in some ways, they're kind of dumb. Their performance depends a lot on what kind of training data they've seen. So one thing I found super annoying was that when I would walk around and then look at the reconstruction of my skeleton, if it couldn't see my head for a while, it would suddenly grow me to be 6 feet tall, because most of the subjects in the training data set were 6 feet tall, and it just figured, well, that's the most likely place for a head. Not only that, but we had this real-time demo where we finally just hard-coded the head doesn't leave the body, okay? Because it was very disturbing during the demo. But also another thing that nobody thought about when they were collecting training data was we have this kind of standard height of deploying a device, 1.4 meters, okay? So when you go and you install a device in someone's home, and by the way, this is a small company that's running, it's self-funded. It never took any investors' money. It became profitable so fast, not very profitable, but profitable enough that it's been running on its own funds, but running very leanly. So everybody had to do everything. And I made 19 trips to Miami to install devices in people's homes, which is not a bad thing for the engineering director to do, except probably would have been 3 or 4 would have been enough. 19 was kind of overkill. Well, sometimes you can't put the device at 1.4 meters. Like there's a couch there, and so you're like, okay, well, I'll put the device at 1.6 meters. Well, what happened when we do that is that the skeletons are all floating a few inches off the ground, right? Or it's like the model learned that the ankles are exactly 1.3 meters below the device, because that was always true, right? So it's like, this is a weird house. Everybody floats, right? So there are a lot of ways to deal with this, but nevertheless, there would just be these funny surprises when there was just anything a little bit different about the setup. Nevertheless, you saw that result. You saw the video, right? When it's working, it really works well. But how do you train a model like this? That's one of the tricky things. So what you could try to do is, well, wait a minute. A human can't label the radio frequency signals. That is hopeless. Like you can't look at this. We don't have any way of visualizing what's going on from the signals themselves. You can't do that. But you could simultaneously collect video and radio signals, and then you could employ human labelers, and that would work, but it would be way too much effort. You can also, there are commercial systems where you put special sensors on the body, and they will give you, the location of the points on those sensors. The problem with that is there's a lot of overhead in setting up the data collection system. And to make the model robust, you need to move this around and collect data from a lot of different people in a lot of different places. And so that was just too much work. And so the solution instead was, well, it turns out there are already pretty mature systems that will take video data and annotate the body, find the people, annotate the body positions. And while our data is going to be not video data, we can use these computer vision systems as the teacher to provide the training data. So that's what we did. We would set up a bunch of cameras, which hopefully you could kind of do very quickly in the room. Somebody would walk around with a checkerboard so that each camera could see it. And then you would be able to tell sort of, okay, what's the exact relative position of each camera, because they all see the checkerboard at the same time. And then we would collect the video, run the video model, not ours, one that already exists, that produces these annotations, pose annotations. And the models we used were two-dimensional. They would take one camera point of view and provide a two-dimensional image, but we knew the location of the cameras, so then we would just merge these to give a three-dimensional image. Yeah?
So quick clarification, will the motion or the movements of normal people be the same as patients? So that would...
That's a good question and unknown. That's a very good question. And my experience has been that sometimes you get surprised and things don't work. So it's something you have to watch out for. Now, fortunately, we are in a position sometimes to collect a lot of data about the types of patients that are in these studies. But it's a good question. That is a question you always have to think about. Yeah, because if your test subjects don't have the conditions, you might get different data. Yeah.
A silly question, why not just use videos? Why RF signal?
Yeah, that is a good question. So there's a couple answers to that. Yeah, one is that people are not always comfortable having a video camera. Now, and we always tell them, oh, okay, we're not collecting video. This is radio frequency, the wavelength's like this, we can't capture your image. On the other hand, you saw it, we can tell what people are doing in the room. So potentially there's a little privacy thing. The other thing is our system works in the dark. Now, of course, you could use infrared cameras, but also we can see through things. So if I'm trying to collect somebody's breathing signal or their heartbeat, and they're in bed with covers on, the radio device can see that and the camera can't. So we can see through walls. We don't actually do that. We never purposely, in any of the studies right now, we're not collecting data through walls. In fact, it's sort of the opposite. When someone goes into the home, they also measure the perimeter of the home, so we can throw away any data that's on the other side of the walls, like in an apartment or something. But those are the standard things, that you can collect different data and potentially it's more privacy preserving. But it's a good question. So we use the vision model to do the annotation, and now we have this big ground truth data set, so we can feed in the RF signals. That's the actual input to the model, and we have the answer, and so we can train the model, and we can say, hey, this is the output of the model, this is the ground truth, and now make your adjustments using standard learning algorithms, and eventually you get a model that requires, in training, we need the video data, but once the model's built, the only input is the RF data. Okay? And interestingly, this student can do some things the teacher couldn't do. This seems like, I don't know, like a lesson from the old TV show Kung Fu or something. There's something special going on here. Okay, so what else can we learn? So far we've just talked about, mostly talked about position and pose. But actually, most of the data we collect is breathing. So here's Fadil again, and we're reconstructing his breathing signal. He is told at some point to hold his breath, and you can see that what is actually being measured here is like something about the distance from his chest to the device. Now, I mentioned at 6 gigahertz, the wavelength is 5 centimeters. When you breathe, your chest is not moving 5 centimeters closer or farther from the device. It's like some tiny amount. So we have to be able to collect data that is accurate enough or sensitive enough that we can measure not even a whole wavelength, like just little changes in phase, and do that well enough. What's really being plotted here is sort of, this is another place where we can talk about interesting algorithms. So we've taken this FFT to get the change in frequency. And actually, we're going to do that over and over and over again. And if the person's breathing, then that change in frequency will, it'll vary a little bit, as you're the output of the FFT will vary a little bit as Fadl's breathing here, but only a little bit. And you kind of look at the components of the FFT, and they're complex numbers. And because we're not even a whole wavelength, they're just like the phase part is just kind of rotating a little bit back and forth. And that's a complex number, but we're trying to plot a scalar. We've got to convert it to a scalar. So the first thing that's done is called PCA, Principal Component Analysis. And what that's doing is, in this case, something sort of the simplest case, taking two-dimensional data, finding the direction in which it's varying the most, and converting that to one-dimensional. So that's what we're doing. We're taking the output of the FFT, and we're doing a PCA so we can plot it in a way that makes sense to somebody who wants to look at a breathing signal. What if there's two people in the bed, and we have two breathing signals superimposed? Then we do something called ICA, Independent Component Analysis. You try to separate, you sort of tell the algorithm, there's actually two signals being mixed here. Do your best to pull out two uncorrelated signals. And now we'll say, there's an algorithm called fast ICA. We use that. And in fact, I tried many different variations of ICA algorithms, including not first converting to a scalar, but like doing it directly on the complex numbers. And maybe that's a little bit better, but it didn't help that much. So FFT, PCA, ICA, kind of classic, basic signal processing algorithms. And then thrown on top of that, there are a bunch of kind of custom machine learning algorithms, like let's say we're just looking at one person lying in bed and we're trying to get their breathing signal. Sometimes they might roll over or toss and turn. And when they do that, like their distance to the device is changing way more than if they were lying still breathing, right? You have to throw that out and say, okay, we don't know what's going on there. So there's like an algorithm that's trained to detect someone moving in bed. And if they move, then there's just a section of the data we don't measure the breathing because we couldn't see it, right? So there's a mix of these well-known, very simple, fast, useful signal processing algorithms mixed in with more sort of custom machine learning algorithms for our application. Okay, so so the measuring breathing we do really well. So the standard prior to the new wireless technology was to wear a belt over your chest. Sometimes people wear it when they go exercising, or you can wear it at night. And I've worn these belts many nights. I'm the #1 guinea pig for this stuff. And, we can really capture individual breaths just about as well as having this belt on, but the belt's annoying. Let's look a little closer. So here's one of these breathing signals, and you can see, when the person's inhaling and exhaling, but if you blow it up, you can actually see individual heartbeats because your chest the distance is changing on individual heartbeats. Now, we don't actually do this in any of our studies, and the reason is to get this kind of resolution, we had to kind of increase the power. And the reason we can't just increase the power to whatever we want is because we've got this radio and we have to conform with FCC standards. So it's not a health issue, but it's an interference issue, and we don't have a license to use enough power to do this. But we can get the breathing signal, no problem. And we know in principle we could get the heartbeats too. Okay, so having a breathing signal is medically useful. So this is a depiction of 4 minutes of breathing of somebody who has very severe sleep apnea. Sleep apnea is a condition where you're lying in bed sleeping and then you stop breathing. And there the participant is breathing, and there the participant is not breathing. So, it's immediately apparent that this person has sleep apnea. It turns out that sleep apnea is a very serious medical condition because it's very hard on your heart to be deprived of oxygen over and over again. So if you have sleep apnea, you should be treated for it. It will prolong your life. So you don't want to have sleep apnea. And so at one point, after a little bit of complaining, maybe a lot of complaining and prodding from my wife about my snoring, I was sent to the sleep clinic at Duke to be evaluated. And when you go to the sleep clinic, we'll see pictures of what they do to you there. But they cover you. You put all these electrodes on, you get in bed, and then they measure your breathing, and really annoyingly, they woke me up at like 6 and said, okay, you can go now. It's like, oh, really? I want to sleep, but okay. So then they came back after the technicians read my data, and I said, well, do I have sleep apnea? They said, well, no. The good news is you don't have a medical problem, you just have a social problem. Okay, so by the way, I'm here staying with Satish, and Satish, I apologize if no one else in the house is able to sleep. It's a social problem. Okay, so here's something interesting. So when you're in the sleep lab, though, yes, they're trying to detect sleep apnea. That's kind of easy because you just stop breathing. Another thing they do is they look at this data from the electrodes, and they measure your sleep stages. Like, are you awake? Are you in light sleep? Are you in deep sleep? Are you having REM? And in the sleep lab, they're looking at data collected from electrodes that are attached to your body. We have determined that you can extract these sleep stages just from the breathing signal. And how did we do that? So we went to the sleep lab, and this is one of Dina's former PhD students, Mingmin Zhao. Okay, he's got a great expression. But that's what they do to you before you get in bed. Then you have to sleep with all that stuff on, right? Mingmin is at UPenn now, and so we partnered with a hospital, and we started collecting data. So we collected the breathing signal, and then we also the hospital, they collected data the traditional way, and it was hand-labeled by technicians. The sleep stages were hand-labeled. And then we built a machine learning model that would try to predict the sleep stages from the breathing signal, rather than from anything from these electrodes. And so here's another one of Dina's former students, Shichao Yu. So this is the idea. We want to get the breathing signal, and from that, the sleep stages, like over every 30-second period, just from the Emerald device. But the model was trained using the data that was labeled by the technicians. Now, here's a figure that you can think, maybe you'll think is good or maybe bad, and that is that if we look at subjects that were taken out, not 100 nights for 25 subjects, not part of the training data, our labels agree with the technicians' labels about 80% of the time, which sounds pretty bad, actually. 80% accuracy doesn't sound so good. But it turns out if you take two technicians and you compare the labels they manually put on, it's about 83%. So it's not that precise. What you're really trying to get is a feel for how many cycles of REM does the person get, and how much time, what percentage of time do they spend in deep sleep? So you might, you can get a feel for that maybe even if you're not perfectly accurate. And one thing I've learned, who knows why, I don't spend much time in deep sleep. And so I was kicked out of a couple of Dina's studies because my data was too weird. So nevertheless, wait, what? Who cares about this? Well, there are a number of clinical trials that Emerald's participating in where they're testing new antidepressants. And one common side effect of standard antidepressants like SSRIs is that they cause all sorts of sleep problems for people who take them. So it would be nice if they could develop an effective antidepressant that didn't mess with your sleep. So they want to know, okay, these people are taking their new medication. Does their sleep architecture look kind of normal? Yeah.
So does this model require calibration on the same person, or can it be transferred across?
Yeah, no, this model doesn't require calibration. I mean, maybe it could be better if it did, but we don't do that. There's just one model that you feed it a breathing signal, and it spits out the sleep stages. Yeah.
Good question. How accurate are the consumer wearables compared to the
So,
like watches and all those reasons?
I guess it depends what you're measuring. I don't think that Emerald necessarily claims that we're that much more accurate. but we don't require you to wear anything. Okay, so we're not sort of arguing that the consumer wearables are inaccurate. We're just saying this is just a little bit different. You don't. We have a bunch of studies where these are Alzheimer's patients, and you can't expect them to remember to put something on or keep it on or whatever. So it's a different axis that we're saying there's an advantage, not necessarily accuracy, right? In general, having something attached to your body will be more accurate usually, right? It's easier if you're physically there. Yeah.
There seems to be many spikes in this figure.
Yeah, so, and I don't, that's a good question. That does seem a little unusual, like a little abnormal. And the spikes are going up to awake. So somewhere between light sleep and awake. And it could be that when Xichao is in light sleep, he moves around a lot. I don't know. Yeah, that's a good observation. I don't know. Anytime you look at the real data, you see weird stuff. All right, so fair enough. I agree. That seems a little hard to believe, but there it is. Okay, so here's, okay, wait, before I show you this. Okay, that's me. Okay, so I'm lying in my bed in Cambridge, and right now there's a lot of action going on, in the pharma industry, trying to develop drugs to treat all sorts of autoimmune conditions, but one in particular, skin conditions, and one that's possibly an autoimmune condition is called atopic dermatitis. They're trying to come up with ways to treat this skin condition. And what they want to know is, if someone's taking our drug, do they scratch less? So we have a model that's specific to counting how often you scratch while you're lying in bed. All right, so now I don't itch too much, so the scratching that you're going to see is artificial. But what we see here is a video, and then down here is the output of the model showing the model's estimate of the probability that I'm currently scratching. And then what we're going to do is we're going to tag events wherever this gets above some threshold. We're going to say they were scratching there. And so let's look what happens. So I'm lying here. You can tell I'm going to scratch at a certain point. And yeah, so the model got it right. It's really pretty simple. It's really just looking for movement at a certain frequency. It's not any smarter than that. But it can see if I scratch one foot against another, and it can even, because it's just looking for that frequency, even if the device is in a position, the device, by the way, is actually over here. It's a little hard to see, but even if I flipped over, and so like my hands were shielded by my body, there would be multipath reflections. It might see it, likely would see it anyway. It doesn't really care about the distance. There would be some reflection that was fluctuating. It would be like, oh, somebody's scratching in this room. Now, the reason we have a video here is we don't normally have this video, but we had a customer who wanted to certify that the measurements we were taking with our device of the scratching of the participants in some big trial were accurate. And so they asked us to build a camera, and they went out and found volunteers who would let us collect both video data and the radio frequency data at the same time. And then we built a video labeling app, basically. And then they did one of these sort of mechanical Turk type of things where they got hundreds of paid labelers in another country to watch the video and label all the scratching events. And two of us every week would do a little sanity check just to make sure that the cameras were working. So we would, for every participant, for every night where they had turned on their camera, and you had to walk up to the camera, press an on button to turn it on, we would watch to make sure that the video was collected correctly. And the one thing I learned that's deeply burned into my head is that people who agree to put a camera in their bedroom at night don't care what anyone else sees, okay? Oh boy. So it was, and there would be, eventually you start to remember these long serial numbers of the cameras, and you're like, oh no, not this one again, right? So like one thing we were very careful about was that within the company, there was a couple employees who interfaced with the clinical side of things. So the way these trials work is doctors recruit participants for these studies. And so we have to get the device into the participant's home. And so there is a place where some of that information is recorded. But if you actually look at all the data that we're collecting in the analysis, there are no personally identifying information, right? So we don't, I don't know where anyone is or who they are, and normally we don't have video, but I could recognize the same camera coming up, and we would say, okay, you watch this one. I'm like, no, I'm not watching that one. So yeah. Interestingly, when you have humans label the scratching, the labels will be a little bit different than what the device says. And one obvious reason for that is the device and the humans can see different things. The human can't see under the covers. The device can see under the covers. So that's okay, because what you're really looking for is you just want to kind of know, like, are they close enough that we can tell, like if someone starts taking the medication, do they start scratching less? I mean, ultimately, that's really what you want. You want to know that your metric is correlated with the effectiveness of the medication or the safety of the medication, depending on what you're trying to do. Or in some cases, some of these experiments were just looking at the progression of disease. They maybe didn't even have a medication. Okay. So I've talked about some of the diseases, but actually there are a whole bunch of different trials going on for different kinds of diseases. So I mentioned autoimmune diseases, and autoimmune diseases that are like skin diseases, scratching is a way of measuring, how severe it is. For other autoimmune diseases, like Crohn's disease, so it seems like, okay, how are we going to measure that with our device? So it turns out that with a lot of these diseases, they're episodic, so that someone it'll be sort of, I don't know, I'm forgetting the words, but it'll be kind of latent and they won't be suffering. And then they'll have an episode where the body starts to react. And what happens, often there's inflammation. And inflammation causes swelling, sometimes pain, and also typically a rise in body temperature. When your body temperature rises, involuntarily, you start to breathe faster. That's a cooling mechanism. It's like dogs panting when they're hot, right? So for some of these diseases, you just look at their sort of nightly breathing, and you can even tell in advance of the patient knowing that an episode is coming, you can kind of see every night, they're starting to breathe a little faster every night. Maybe their body temperature is rising. So we've, studying some lupus, Crohn's disease, other autoimmune disorders, and mostly they're looking for whether we can detect inflammation through the breathing signal. I mentioned atopic dermatitis. The Parkinson's and Alzheimer's studies were typically more looking at gait or activities. What are they doing? So let me say a little. I'm about to finish here, but feel free to ask questions. A little bit about So I've done this a couple times now. I've gone thinking I was going on sabbatical to MIT and then getting sucked into a startup company. And so that's what happened here. I went up in the fall of 2019, and actually Emerald took a while to get off the ground. They had built prototypes at MIT in 2015, but they spun out of MIT as a private company in 2019, and I was the first person who came in who wasn't part of that original team. And I joked that they hired me to manage them, which wasn't really not true because they were unmanageable. Yeah, so very shortly after that, Emerald got a big contract to collect data in a study for a foundation that's devoted to finding treatments and cures for a certain disease. And the contract was kind of front-loaded, so it gave us enough money not only to build infrastructure and build devices, but also hire some people. And Emerald designs its own hardware and writes all its own software. I mean, of course, we rely on a lot of public domain software, but open source software. But Emerald really does everything end to end. So the radio is designed by Emerald, and over the years, a lot of other stuff has been kind of baked into the device. So there's an accelerometer in the device. Why is there an accelerometer in the device? Any ideas why we might want that? The thing is, sometimes the participants drop the device, and they don't want to admit it. So when the device is acting wonky, the first thing you check is, did somebody drop this on the floor, right? And an important decision that was maybe a mistake was Emerald decided really early on, we're not going to put screws in anyone's wall, okay? So the device is held to the wall using these 3M command strips they're really designed to hold posters to the wall. So that means that we really care about the weight of the device, but also the texture of the wall and how long it's been on the wall, and most importantly, it must be removed from the wall very carefully, and you don't want to leave it on too long, because these command strips, a few times, like, you know, I'm in Miami, and I go into the house getting ready to carefully take the device off the wall. And they're like, we took it off for you already. And I was always like, oh no, because then I look, and their drywall is totally destroyed, because they just, you know, ripped it off the wall. You have to pull on the command strips, right? So I'm really kind of on a tangent, but this is going to be a fun tangent. So I went to Miami 19 times, okay? And the participants in these trials are not paid very much to participate. It's really not much. And I think the reason for that is they don't want people to take health risks for money. Nevertheless, it seemed to me that many of them, maybe the majority, were doing it for the money. In fact, some were very angry that I didn't show up with the money. And I would say, well, it doesn't work that way. The clinic is supposed to give you a check. I'm not carrying cash, okay? Well, one of the consequences is that they were often in kind of tough neighborhoods, right? And so I'm driving around with my rental car with a bunch of boxes full of these devices in the back, and I'm going from house to house. And weird things would happen, like, well, so I don't really speak Spanish, and almost all the participants in Miami were Spanish speakers, and many of them didn't speak much English. So I had a translator, Manny, back in Cambridge on the phone, and Manny says, she says the door's unlocked, just let yourself in. And I'm like, Manny, you guys have sent me to the wrong house 3 times. I'm not gonna open anybody's door, right? You don't know where I am, but I'm not doing it. Like, I'll sit in the sun out here on the sidewalk for 5 more minutes, but if no one comes to get me, I'm leaving, right? So that's the life of a, you know, like, I know what it's like to be a cable TV installer. It's not easy. The vast majority of the participants, though, were super friendly, and like, I would go and each one would give me this very strong Cuban coffee. And by the 4th house, my head felt like it was going to explode. And so then at the end of the day, I would go windsurfing in Miami. That was good. Anyway, so Emerald got going 2019. We got our first customers. And so today, I don't know, a lot of the customers don't want to, they don't want to give their names, but it's a mix of pharmaceutical companies, including large pharmaceutical companies, and foundations that are studying different diseases. And so in clinical trials, there are different types of trials, so like phase 1, phase 2, phase 4. And Emerald's goal is to eventually get the device certified so that the data collected by the device can be used as evidence and presented to the FDA as part of the case for approval of the drug, which means, you know, evidence that the drug is effective or evidence that it's safe. It's not yet certified that way. So that's a long process, and that's underway. But the device can be used internally by the pharma companies so that they can get a hint maybe early on, does the device seem to be safe, or does the, sorry, not the device, the medication. Is the medication safe? Is the medication effective? Eventually, if you want to be used in, phase 4 clinical trials, you have to get that kind of certification. And so Emerald's working on that. But nonetheless, it's already out there. It's being used, being used in real trials. It's not quite used as, it's not actually certified as a clinical endpoint is what they call it. The other thing is, and this is super important, the Emerald device is not considered a medical device, okay? Because it's being used, it's not being used to diagnose or alert anybody to a medical condition. Data's being collected, and it might not be looked at for months afterwards to determine what's going on with some medication, but it's not being used as input into any kind of treatment program. And so that would, to get certified as a medical device is also a whole other thing that you would have to go through, which might happen someday. A lot of people ask me, okay, fine, but it seems like this is kind of a niche market. Like your device is being used in some clinical trials, and yeah, you've got a half dozen big pharma companies, but why not sell this to consumers, okay? And so that's really interesting to think about. How would you scale this company? And so the first answer to that is, it's really expensive to run these clinical trials, and the pharma companies may spend $50,000 to $100,000 per participant in the trial. So they're not very price sensitive. If you say, okay, yeah, we want $1,000 a month. By the way, I'm making that number up. I don't know what the number is. I wasn't involved in that, but it's some big number. They're like, okay, right? But if the next natural market would be, instead of pharma companies, insurance companies who want to have the device put in the home of one of their members, and they'll say, we'll give you a discount if you let us collect some data, because maybe it's an elderly person or someone with a chronic health condition, and they want to know, like, you know what, you're only sleeping 3 hours a night now. You need to see a nurse before you end up in the emergency room. That's a natural, really big market, but they would only do that if it saved them money. And that means the price would have to come way down, right? And so you'd have to be able to scale up to being able to build a really large number of devices and run everything more efficiently. And so we're not there yet. There are natural large-scale markets, but Emerald isn't able to do it at a price point that would work yet. Okay, well, thank you.
The second person to go to Miami also.
Yeah, and I wasn't the only one. We took turns, but only one at a time. Yeah. Yeah.
Thank you.
Thanks. Yeah.
It uses battery, or it has a cable for electricity?
It has, well, both. Okay, so if we go, by the way, that was all interesting, but I'm about to show you something that you should never forget, because it's the most important thing you're going to learn from this talk. If I want to go back to slide 2, I can type 2 and hit enter, and there we are. Okay, so there's an adapter there. It's I don't know, 12 or 18 volts or something. But there's also a battery in there, so that if the power is interrupted, after like 30 seconds, it does a clean shutdown. Yeah. It can't run for long, though, on the batteries. Yeah.
What are the most expensive part?
Okay, so inside the device, probably the most expensive part is the custom radio board. And we designed that, and we have those components, we have a bunch of different vendors in other countries who build individual parts, and then it has to be assembled. So the custom radio board is probably most. Then inside, and I don't think this is a secret, there's an NVIDIA Jetson Nano computer. It's about $100. And then there's also this custom battery backup circuit we built. Those are probably the 3 most expensive things. Then there's some little things. I mentioned there's an accelerometer. There's a light meter that can only tell, like, are the lights on or off in the room.
No DSP?
There's no DSP. All of that is just done in software on the Nano. Like the,
Interesting.
yeah. There's like an FPGA on the board, but really, and it's kind of a DSP, but only in the sense that it's sampling the signal and then feeding the raw samples into the nano, and the nano is doing all so then the job of the nano is basically take the signal for each frame from all of those different transmit antennas and perform multilateration and convert it into one depth image, and then compress the data and then send it up to the cloud. And then all the interesting processing takes place in the cloud. So one of the things that matters though is you do have to have a good enough Wi-Fi network to support this steady upload of data. And it's understood that sometimes the network may go down, so I didn't mention this, but there's also an SSD in the, a couple, I don't know, maybe a terabyte or something of data. So you could store several, 6 weeks of data if they really lost their network. And we don't like that, because then we can't tell if the device is even, but there's also a cellular data modem inside. Because as a last resort, we got to be able to SSH into the device and figure out what's going on there. Yeah.
What would it take to do a true edge AI for this whole thing, to not upload the data to the
Yeah, so that's a good question, and we have experimented with that, like trying to move more of the processing into the device, especially if that would let us upload less data. And I think the answer is, the nano is kind of limited, but it can do more than you might expect, right? You can run, it's got a GPU, you can run machine learning models, but we're already kind of pushing it just doing the signal processing. So I don't really know the answer to that, but I think more could be done. We're just, at the moment, that's not how the computation is split.
But maybe spin the question the other way around.
Yeah.
Is there a need for that?
So if you really just took the raw data and tried to send it up, you couldn't do that, right? It would be, you can't, a lot of the participants, like they're low-income families, they don't have like gigabit per second upload like I actually do at home. And I had 2 teenage boys, and they were big gamers. And they would constantly complain to me about the quality of our home network, which is quite irritating to me because I'm a computer networking expert. And they'd be like, Dad, our Wi-Fi sucks. So what are you guys talking about? I have given each of you a direct port into the AT&T router. So you're not even using Wi-Fi. You guys don't even know what Wi-Fi means, but you're not using Wi-Fi. And the problem is a server somewhere. And they're like, okay, Dad, then Akamai must suck. Okay. Any other questions? Hey, Cliff, yeah.
Are there any algorithmic questions that you wish could be answered, or that would help this technology?
Yeah. Yeah, there are, although I think maybe some of them are more in the machine learning domain. But just as an example, okay, it's really annoying, this idea of having to wear the ankle bracelet for 2 weeks. It would be nice if you could just say, okay, I want you to walk back and forth in front of the device 10 times. And that's it. Now we're going to build a model, and we're going to differentiate you from everybody else. Okay, and we're very far away from being able to do that kind of thing. But there are a lot of machine learning algorithms for sure that would be nice to have.
You need 2 weeks of data to calibrate?
That's what we collect now. I can't tell you, maybe you could do it with less, but yeah. So it's interesting, if there's big height differences between the people, you can figure that out pretty quickly, but there isn't always. People tend to marry people the same height. I don't know. So it's kind of so yeah, you have to kind of look for other things, and you need a lot of data right now. Yeah.
Okay, so are there no privacy implications of these things? I would have thought, I'm not sure I like my neighbor having a device that can look through my walls.
Yeah. So, well, for sure there are privacy implications. Absolutely, they are there. And there's privacy of the participant who's volunteered. Even though they volunteered, they do have we want to respect their privacy as much as possible. Yeah, I don't know, like anything else, your neighbor might not be happy if you put a camera on your door and you see them every time they go into their door as well. We do our best. We really do carefully measure the room, and we throw away all the readings that are outside the boundaries. So we, as far as I know, we don't collect data from people who aren't in the home where we have consent. But sure, you're right. There are real privacy
So
concerns.
there are no regulations forbidding this. Like, me using a camera, a device that listens through the wall at my neighbor's home. As far as you know, there are no regulations.
So, okay, so I don't know about, I guess it depends where you are, but as I said, we don't listen through the wall. That data is thrown away. We don't collect it. We don't look at it. Yeah, well, you have to believe me, but we certainly do our best. We don't want to see that data. It doesn't help us, and it obviously would be upsetting if we collected it.
Yeah.
So, I think the rules may vary from place to place, but we are not collecting that anyway.
Oh, wireless routers are talking through walls.
Wireless routers are talking through walls. That's a little bit different than measuring stuff. You're definitely bleeding stuff through walls. You can listen to your neighbor's network traffic. That's a little bit different because it's their fault that they're transmitting it. But yeah.
So you said outside the square, wherever you measure, it's all thrown away. Is it thrown away at the device? Or
Yeah, they're thrown away at the device.
At the device.
Yeah, because the device is we're combining the signal from all the transmit antennas and building this like heat map, and we throw it away. Yeah.
I wonder what's the main challenge on the system side. I understand there are many challenges on the machine learning side, like how can you recognize the humans doing what stuff, but
Yeah.
what's the main challenge on the system side as a system builder?
Yeah, so, interestingly, about half of the engineering effort is going in on the system side, and then about half of the effort is going in on the sort of machine learning, we call it analytics. The main challenges on the system side are, right now, things like reducing the cost of the device, reducing the amount of data that has to be sent upstream, reducing the weight of the device, and most important, making sure you never lose any data. And then when you process the data, you can create a provenance so that you're 100% sure when you present an output what data was read in and which version of the code was used to produce the output. And okay, so and you have to know, like, okay, so I have some stream of data coming from some participant. Sometimes you do lose data. You need to know for sure I lost this data, and then I start it over again. So, but I would say the number one priority is never lose any data. But all those other things are big engineering challenges too.
The key idea is to make sure that we are correct, or to prove to some other people that we are correct. Which one?
I don't really see a difference between that. But ultimately, as I said, we want this system certified by the FDA as an endpoint for clinical trials. We want to have a very strong argument. And in fact, you have to freeze the software. They certify a particular version of your software. So we need to be able to say, yeah, we produced this output with the version of software that was certified.
Maybe what he means is that you could have two modes. Like if you're in a mode where it's a device used by the insurance for prediction purposes, maybe you can throw away a lot of data which you cannot do as an endpoint.
Yeah, so there are definitely times where you just say, look, I don't want to pay for storing this data, I'm going to throw it away. That's totally okay. But you want to have the ability, when you don't want to do that, to know for sure where your data came from and that you didn't lose any.
Right.
Yeah.
My watch also analyzes the way that I'm sleeping, and
Yeah.
gives information about it. I guess mostly from heartbeat and some movements, right?
Yes.
And I know that it's completely inaccurate, right? In most nights, it's completely off.
It's off.
It's off completely.
Okay.
But my question is, assuming that it will be improved, I mean, how much this radar is more accurate than
So as I said before, I'm not necessarily claiming it's more accurate, okay? The biggest difference is it doesn't require you to wear a device.
But for example, a watch I'm wearing anyway.
Yeah, but you're a person who can put a watch on. You don't have Alzheimer's disease, right? So yes, for many people that wouldn't be a big difference, okay? There's some things the device can do maybe the watch can't do as easily, like reconstruct your pose, or Now, the other things it could do, like you could imagine measuring scratching with a watch, measuring heartbeat with a watch, maybe even measuring breathing with a watch. So many things. I'm not saying you couldn't measure as accurately as a watch. The main thing is it's passive, and then I guess the other thing is a big effort is going into kind of scientifically proving that it's accurate so it can be used as data in clinical studies. Although to be fair, the watch vendors like Apple also have done that. Yeah, the Apple Watch is approved for certain metrics. Yeah. Yeah, Raj.
Sort of on a related note, and maybe expanding on that, combining different kinds of data, so the Emerald data with some other data, could that be more effective, or more broadly combine? There might be privacy issues, but looking at Emerald data from many different patients and trying to discover something that was not known before.
Yeah, so it's a very attractive idea. Like, okay, this is one type of data, but the participants in these trials, typically other types of data are also being collected. So most commonly they collect data from surveys, but they also will sometimes collect like blood samples, or they'll have a nurse come in and take other measurements of what do you call it? I don't know, heart rate, blood pressure, whatever. So in a number of the studies, we've made agreements with the pharma company or the foundation, whatever, the doctors, to exchange all data afterwards. So then we can look and see, is there more we can learn when we combine the data? Because we should, right? It can only help, right? At minimum, it's a good sanity check, but sometimes you might be able to learn even more. Yeah, I mean, I think a good example is sort of observing that you don't need electrodes to predict sleep stages. You can't really you can't figure that out till you've got both data together and you start to realize that one is good enough to predict the other. Yeah.
So this one is mostly of a study of what is happening, and is there any event being triggered? Okay, the nurse should do something in case of a certain event.
So we're not doing that right now. And obviously, you can imagine the simplest thing you can imagine is like fall detection. And a device like this could detect falls. I don't think that's so hard. But we're kind of shying away from that because then you start to veer into being a medical device, right? If the device is being used to guide treatment, then the standard is different. And you might want to do that someday, but so far we've avoided doing it. And it's definitely not being used for that today. Yeah.
Great.
Okay, thanks. Yeah, thanks for that.
Thank you. I think Tavi spoke about this at SODA, like in 2016 or 17, actually.
Yeah, it's been a long time.
Yeah.
But it's turned into a real product.
In case it sounds familiar anyway.